Thank you for coming out tonight to this President's Innovation Forum and Innovation Talk series. This is an interesting presentation we're going to have on team neurodynamics. We have two very important people with us tonight who are going to share their expertise. The first is Ronald Stevens. Dr. Stevens is a professor emeritus at UCLA School of Medicine and a member of the UCLA Brain Research Institute. His recent research has focused on using EEG-derived measures to investigate team neurodynamics in settings as diverse as submarine piloting and navigation by Navy teams and high school problem solving. These studies are leading to quantitative teamwork models showing how teams cognitively organize in response to environmental and task changes. Our second speaker is Mr. John Combe. In 1996, he founded Team Results with ex-fighter pilot Peter Ring. Originally, they did so that they could both learn more about what worked and what did not work with people and teams. Team Results grew rapidly and now runs team and leadership development and organizational planning programs on 4 continents. In 2004, he wrote a bestseller on success and leadership called Crocodile Charlie and the Holy Grail, which is published in 7 languages and 14 countries. And without further ado, we're going to introduce Mr. Combe, and he's going to talk a little bit about the machinery that you see here today.
Well, folks, first of all, good evening, and thank you very much for coming. Second of all, just for novelty, the entire next 15 minutes of tonight will be delivered in an Australian accent. I hope that's okay with you. I have great difficulty speaking in any other kind of accent. My name is John. I quickly want to introduce some of my colleagues as well, and then some young people that are going to help us with the experiment after that. But my colleagues first, and they'll give you a wave so that you know who you're looking at as we go through. First of all, Dr. Leslie Gruss. She's from Team Results USA. Then comes Michaela Quiroga. Michaela is from the Montgomery College Hillman Entrepreneurs Program and is interning with us. And then Andy Tobin. Andy Tobin is one of our technical directors, so he's here to make sure that all the equipment works and that I don't do anything I shouldn't. And again, my name is John. I also want to introduce some young people who are helping us tonight. First of all, let's begin with Alejandro. Give us a wave, Alejandro. These are all Montgomery College students and they have various roles to play. Alejandro is going to be one of our race callers. What that means I'll explain in a minute. May I please introduce Jamie? Nice cheer, thank you, sir. As the flag in her hand indicates, Jamie is the other of our 2 race callers. Next, I'd like to introduce Bibiana. Nice cheer. You'll see Bibiana's wearing something on her head, and I'll explain that in a moment. Also wearing the same kind of equipment on her head is Sandra. Give us a wave, please. And thank you very much. Folks, I'm not a scientist. I'm a practitioner. I'm the CEO, as I think Darren mentioned, of Team Results USA, and it is our job to actually run team and leadership programs for corporate and government clients and their simulation-based face-to-face programs. But the science that underlies what we do is based on large part on recent developments and certainly on developments in neurodynamics. And therefore, it is sometimes my job to explain to senior people in government and industry what the science is and what the basis of it is. One of the big problems we had with that is that the science with team neurodynamics is so new and so exciting, and a person my age would call it space age, I don't suppose anybody else would, but so modern that it can sound like rubbish, particularly in an industry training, leadership training, where there is a tremendous amount of rubbish. People expect it, and there's a danger then of it getting lost in the noise. I had a conversation about this with Professor Stevens about a year or 2 ago, and he told me the only way to show people is to show people. So that's what we're going to do. We're going to show you. This is a demonstration of concept, a simplified version of the much more sophisticated scientific equipment Ron and his team are using in the Brain Research Institute at UCLA. If you look on the screen, you'll see an enlargement of the kind of headset that Bibiana and Sandra are wearing. This is an EEG headset. EEG stands for electroencephalography. It's from the Greek. Roughly speaking, it means listening to electrical signals from the brain. So if you look at that person, you'll see that above their left eye, there's a little target. That's an electrode. It's sitting on the skin just above their eye, and you'll see that clipped to their left ear is a little clip, and that's an electrode. And what that device is measuring primarily is alpha waves produced by the brain between those 2 points. Then there's a little thing on the side that transmits it by radio to a piece of equipment. The piece of equipment, in case you're wondering, is right here. And that piece of equipment controls a toy car. And Andy, if you'd be good enough to step over there and pick up the toy car and give it a wave. So this is a toy car, and the toy car is controlled by a car controller. Let me explain to you how that works. There's a box on this table, and there are lights on the box. That's what we have Alejandro and Jamie for. They are our race callers. They're going to give you a running commentary on the lights, but this is what they're seeing. We're going to calibrate these devices, which takes a few seconds. It'll have to be patient while we do that, although it's actually interesting to watch. Not quite yet, but in a minute we will. And Michaela's our EEG tech, and she's getting in position. We're going to calibrate these devices, but when we're going to ask both people to concentrate as hard as they can. What that means is to make their brain do as much work as they possibly can make it do, and also to engage as much as they can with the subject matter. Some people do sums in their head. We've got one person on the stage whom I won't identify who recites ancient folk tales in his head from memory to drive his brain to work more. There's somebody I know from the Secret Service who wiggles her fingers. Either way, if they're successful, here's what happens. If person one raises their brain activity a little bit, they'll get a red light. If they raise it a little bit more, they'll get a yellow light. And if they raise it to the max, they'll get a green light. If they raise it to the max, here's what the toy car will do. It will go forward and right, forward and right. So, of course, if that's all it's doing, it will go round and round in circles. Now let's think about person two. Let's have person one do nothing. Person two begins to concentrate a little harder. They raise their workload and engagement. They get to the yellow. They raise it to the max. They get to the green. I'm sure you can guess what happens. Yes, the little car will now go forward and left, round and round in circles. I'm sure you can see what's coming next. If we can get person one and person two at some point to raise their neurodynamic workload and engagement to a high level at the same time, then this will happen. Both are red, and then maybe both are yellow, and then both are green, and of course the car now is going to go straight. Well, you'll see that Andy's put the little car in the middle of the circle. The objective of this challenge, get out of trouble. Get the car out of the circle. They'll only be able to do that if they can raise their neurodynamic workload and engagement to a high level simultaneously. When they succeed, I hope you'll give them all a big cheer. Right now we're going to calibrate the headset, so Michaela, when we're ready, what Michaela's going to do is ask them to close their eyes and get as calm as they possibly can, get as relaxed as they possibly can. And I'm going to stop talking while she does that. I'm going to have to go over and help Michaela. Be ready for about a minute of just watching us up here in silence, calibrating the system, but that's what's happening. Once the system is calibrated and working, I'm then going to ask Andy to turn on the car, and our two race callers are going to give you a running race call about what's going on. Be patient, please, for one moment, because we have to switch the system on. This is real technology. So, we're not switching it on yet.
No, yeah, it's on.
Pardon me?
No, it's not on. It's just attached to the head. It goes on.
Okay, right. So let me calibrate it, and I'll tell you when I'm ready for you to calibrate. Okay. Person one first, right?
Mhm.
Okay. All right.
Just continue relaxing. Just rebreathing.
Okay. Now, if both of you could please open your eyes. the device is working. The race callers, please take over. They're going to give you a continuing race call. It's going to be very rowdy. They're going to yell.
Red.
Is the car on?
Come on, red. You got yellow.
Andy, is the car on?
Yellow, green. You got green. The car.
Red. You got red.
Still got green.
Still nothing
Still
right
got
now.
green.
Nothing. Red.
Still green. Come on.
Red. Yellow.
Okay, just yellow now. Back to red.
Yellow. Red.
Red. Still got red. You got yellow. Get to green. You got green.
Red.
It's working. Loud, louder.
Red.
Red.
Focusing as hard as possible.
Yell it out louder.
Keep your eyes open. Keep your eyes open. Focus. Focus. Green.
Red. Yellow.
Green.
Thank you very, very much. And Michaela, feel free to deconnect them. Before we go any further, before we go any further, what do you say we thank our race callers and we thank our Don't go yet, guys,
Thank you. Don't go yet.
because
Good job.
I have for you some presents.
Good job.
Jamie, come back, please. Come back, we love you. Oh. Jamie, thank you very much for your work. Congratulations. Well done, well called. Alejandro, thank you very much for your good work. Well done, well called. Viviana, please come forward. Thank you so much for your great work. Well done. And Sandra, thank you for your patience and doing this to us. So much to do. Congratulations, Sandra. Thank you. What fascinates me about this is that we can actually watch the living brain as it operates and learns. You were watching their brains learn. First it didn't work and it went this way and that way and then it did. You're actually watching the brain. There's no theory or theorist in between you and what you're seeing. You're actually seeing the electrical activity of the brain. I think that's the biggest change in psychology since Freud. As I said, I am not an academic and I want to stress that, but just practically as a practitioner, I think this is the biggest thing to happen, certainly in my lifetime. It's now my very great pleasure to present UCLA's Faculty of Medicine, School of Medicine, Institute for Brain Science, Professor Ronald J. Stevens. Professor Stevens.
Great, thanks, John. First, I'd like to thank Dr. Campen for the invitation to speak here at the Innovation Forum. I think that's really important. And I want to thank you for coming out tonight as well and listening to what we have to say. So for the next 15 minutes or so, what I'm going to try to do is walk you through three concepts, rhythms, entrainment, and entropy, that are kind of the building blocks of team neurodynamics. And we're going to use these to give you some insights into the science behind what John was doing. So the title of this presentation is In the Groove or Out of Sync. And these are really the poles of teamwork. And most people can recognize a team in the groove, but it's really hard to predict when they're going to lose that rhythm. And if they do lose that rhythm, how are they going to get it back? Or if they'll ever get it back. But what if you could? What if you could actually predict how people were going to do, how teams were going to do in the future? How would this influence the assembly, support, training, and in particular, evaluation of teams? So what we have here are two instructors watching a surgery team perform a simulated surgery. And we work with healthcare teams, we've worked with submarine navigation teams, and when we began to study brain waves in these teams, I'd often ask the instructors the question, how is this team doing? And the answers I got back were average. Sometimes I'd get maybe above average, sometimes maybe below average, but it was a very tight range. And we wanted to actually begin to devise more quantitative measures that would separate out these teams and actually give us some type of way of turning the measurement of teamwork into more of a science. So what would be the ideal performance measures? Well, first of all, you'd want something that's validated. So somewhere down the line, you're going to have to compare whatever measure you develop to the gold standard, which are expert ratings currently. You'd want them unobtrusive. You don't want to interrupt the teams in any manner from their teamwork. Quantitative, that's big on my list. Objective, that's one of the potential limitations of having outside raters, is it's often subjective, and you want them to be reliable. But once you have this, then you can begin to make comparisons across teams, the experience of teams, novice-expert differences, different training sites. The military has training sites, the submarine force in Hawaii, up in the Pacific Northwest is the training equivalent at these different sites. Training protocols. Are there ways of actually accelerating the training of teams? You can't measure that without some type of quantitative objective measure. And also team composition. Do you want to get rid of this person and then swap somebody else in? So just to give you a sense of time, this is a time scale of training events, going from neural events that are on the milliseconds or tens of milliseconds, all the way up to the completion of a training course for submarine teams, and this is on the order of 10 to the 7 seconds. So when you're looking at this span of 10 to the 7 seconds and you want to develop a measure of teamwork that satisfied our design criteria, where do you go? Well, first I should say, over on the 10 to the 7th area, this is kind of where John lives, because he's involved in the practical training aspects. Way over on the left-hand side is more where I live, which is down in the milliseconds, seconds, and tens of seconds. And so we wanted to find a measure that would actually span both of these worlds, that would make sense to trainers so that they'd want to use it, but yet at the same time was theoretically grounded in the science that you could actually build on it as a theory. And we decided to go towards the neurologic basis. Teams have rhythm, we already mentioned that, but also there are brain rhythms running around in everybody's head all the time. And so, for example, many of the brain waves that are associated with human cognition are in the range from 1 to 40 hertz, and a hertz is just a cycle per second. So down at the lower end, there's the delta waves, which are mainly found in deep sleep. Coming up a bit, there are the theta waves, which are more involved in memory, navigation, spatial processing. Both of these are pretty individualistic events, and so we didn't necessarily think we would find teamwork measures in these bands. The next band up are the alpha waves, which are a central component of John's demonstration that he showed here. And while alpha waves are usually for attention and prioritizing stimuli, there are also dedicated markers in there. For instance, one set of markers is probably firing in your heads because this one fires when you listen to a lecture. This one turns off when you get in a face-to-face conversation with people, and another marker. So there's a difference between synchronous and asynchronous communication as far as the brain is involved in communication between people. When you get to the beta region, which is the 16 to the 30, included in this are the so-called mirror neuron cells. And so they're both motor cells and mirror neuron cells. So if you start tapping your finger, if we had some EEG on your head, kind of right a little bit in back of the vertex there, then there would be brain waves lighting up as your finger moved like this. Now, the interesting thing with mirror neuron cells is if you watch my finger going like this, those mirror neuron cells are going to click on and off in your head too. So it's not only the motion, but it's also the imagination of the motion or the perception of the motion. It mirrors it back. These two, in the alpha and the beta, are really pretty powerful communicators of the intent of other people. So the last band are gamma, and this is attention, memory, encoding, retrieval, and these are very fast. They're anywhere from 30 cycles per second up to 200, and they often piggyback on the beta and gamma, and we'll have more to say about that shortly. So this is just the background of the rhythm part of the presentation. But I did touch a little bit on entrainment, and that's where we're going now. So on the left-hand side, what I've shown here is a segment of time which is receding away from you, and the x-axis is the frequency going from 0 hertz up to 20. So this is going through the delta, theta, alpha, and beta region. And if you start to play a sound at 10 cycles per second, then after a short period of time, the 10 cycles per second frequency in your brain is going to start clicking, and it will do it to everybody in here. So sound is a very powerful entrainment force of brain waves. The same thing with the flashing strobe, the so-called flicker effect. The brains will entrain to this. Or you watching me wiggle my finger, another part of your brain will become entrained for this. So the waves and the strength of the waves in the brain can become manipulated by the external stimuli that it gets. Now, a researcher at Princeton, Yuri Hasson, took this one step further, and he had audiences smaller than this, but nevertheless, audiences watch scenes from the good, the bad, and the ugly. And what he found was that when scenes were played, a sequence of scenes were played to these, the audience members, different parts of their brain lit up in synchrony. And so people's brains can become synchronized by very complex events, and in this case, by ones that are very emotionally laden. So what does this have to do with team neurodynamics? Well, our hypothesis was that teams become entrained by the rhythm of the task and by the rhythm of the teammates around them. And that these entrainments can be picked up as synchronies across the, in the EEG stream. And once we can detect them, we might be able to find ways of quantitating them. And finally, the last hypothesis we had, which may not be intuitive, but we can get into it, is that better teams will actually have fewer periods of synchronization. So now I'm going to branch off a little bit and talk about how we create a neurodynamic history of a team. So what I've shown here on the left-hand side is a histogram of the EEG power of a registered nurse, the RN, a scrub tech nurse, ST, and a anesthesiologist. And at this particular point in time, at this 1 second interval, the registered nurse is low, the scrub tech is high, and the anesthesiologist has an average level. Now, if this team were very synchronized, the next second, it would look exactly the same. The registered nurse would be doing their thing, the scrub tech and the anesthesiologist would be doing their thing. So if we follow the performance of this team over time and look at every single second, then the combinations that we get create a map, which is shown in panel B. And what this does is it just shows the relative level of the EEG signal for the three team members. And this has a topology. In the upper left-hand corner, everybody's more or less low. And at the lower right-hand corner, and particularly in the bottom row, then everybody is high. So we can number these symbols, 1, 2, 3, 4, 5 at the top, and then the second row is 6, 7, 8, 9, 10, 11 through 15, and so forth, down to 25 symbols. So what can we do with these symbols? Well, linear histories are very common in nature. So if you look at protein sequences, they're just a linear sequence of amino acids, but yet this linear sequence folds into very, very complex structures which have an entirely new kind of function that emerges from it. And we believe that lining up these neurodynamic symbols over the period of a performance will also provide us a functional history of the team. In other words, the neurodynamic history of the team will be written within that sequence. And so what we did is created such histories, and then one thing we can do is just look at them. And so in the figure on the right, we have our 25 neurodynamic symbols, 1, 2, 3, 4, 5, 6, 7, 8 on the y-axis. And then the x-axis is the performance over the simulation. Now, most of the simulations we work with have three parts. There's a briefing where the goals of the the goals of the simulation are outlined. Then there's the scenario, and then there's a debriefing. And you can tell from this figure that during the briefing, the symbols up at 1, 2, and 3 are very highly expressed, which means that the team at this point in time had low EEG levels for this particular EEG frequency. When it went to the scenario, then it reversed. Then the levels of these EEG signals went much higher, symbols number 24 and 25, and then during the debriefing, they pop back up again. So what this told us is that the signals and the histories that we're collecting are very sensitive to major changes in the task, the difference between a briefing, a scenario, and a debriefing, and that this is at the team level. So we're measuring the synchrony of the three members of the team at this point in time. There's also a place in the red about halfway through where there are a couple of blocks where there's a high level of synchrony right around symbol 6 or 7. And this indicates that the state of the team switched. And this happened to be when there was a breathing tube being inserted. Now, looking at these maps will drive you crazy. And so what we wanted to do was to find a way of actually quantitating them. And this is where entropy comes in. And entropy is borrowed from information science, and it's a measure of the uncertainty of symbol distribution within a certain string. And so if we have 25 symbols, if every single symbol is expressed in this one block, then the entropy is going to be high. Whereas if only 5 or 6 or 7 symbols are expressed, then the entropy is going to be low. And so that's the trace that you see in the middle. And what that is giving is a second-by-second readout of the entropy and the neurodynamic fluctuations of the team as they went through these simulations. And this can be quantitated. We can quantitate it over a whole performance. Now, what I've shown you here is how we go about getting neurodynamics at one frequency, one of the 40 frequencies, and one of the 20 sites on the scalp. And so if we want a scalp-wide view, then we actually have to do this about 800 times. And when we do that, we actually find colorful maps like this. And so on the left is a healthcare team, which was a fire in the operating room scenario. And the time runs from the bottom up to the top. And down at the bottom, we show the 41 hertz bands. And the regions of the yellow and the blue are the periods where the team was highly organized. And during the scenario part, while they're looking at the IV line or counting clamps or starting the operation, there's a lot of synchrony within the 10 hertz alpha band as well as within the 20 hertz beta band. So from this, there would be a lot of communication that's going back and forth between the team members. And also, it's likely there's a lot of mental imagery going on as to what is coming next within the scenario. Over to the right is just a similar example for submarine navigation teams. And the contrast here suggests that it's actually the face-to-face interaction in the submarine teams which may be more important than mental imagery. We have tasks with high school students where mental imagery plays almost a complete role and the actual face-to-face plays very little. So this is telling us if you want to begin to design simulations to test the team's mental imagery or their face-to-face communication, you can use these types of markers to see how the team is responding to it. So here we come to one of John's teams, and this was a study we ran with him where we actually had 4 different people running an individual wheel. So this was a prelude to running this by the brain. And one thing that's quite interesting is there's a fair amount around the 10 hertz to begin with as they start to get going. And then there wasn't that much. There was a lot in the gamma in that the task that he just showed involves an awful lot of concentration on the individual's part. Now, this was the first performance that this team had played together. And so from the maps that I see here, they're working very hard on their own task and less, per se, on the team task. Right towards the very end, right around 350 or so, all of a sudden the band begins, beta band begins to light up. The team becomes synchronized in this area. At this point in time, and we've seen this reproducibly, the team anticipates making a hit. And so now all of a sudden they're on the same wavelength with regard to getting to the goal. And it's a different form of synchrony that they didn't have earlier. So what can we do with this? Well, if you think about an absolutely ideal, perfect team, theoretically, every individual would know the task so well that they'd know what's coming next, and they'd know their teammates so well that they would know what their teammates are going to do. And so it should be perfectly smooth. There's no blocks or obstacles whatsoever. But let's say one person on the team starts to lose the plot because they're not well trained. So now the dynamics are going to get disturbed a little bit, and things are going to begin to slow down, and the other team members have to slow down their pace as well in order to accommodate this person. And you get a cascade effect. And so we start to see more persistence of rhythms in less efficient teams. And this is reflected in the entropy levels by depressions. And so novice teams have higher magnitude or greater frequency of the fluctuations, and the fluctuations persist longer than do expert teams. Expert teams understand the situation, that they float along very nicely, and when they need to communicate with each other, then it's done in short bursts, and then they go back to their task work. And so we end up with a neurodynamic profile that's much smoother. And so finally, validation. Can we begin to make associations between ratings by expert team or expert observers and these neurodynamic measures that we have? And we've done this with two different groups of teams. The healthcare teams on the right, there's a standardized observation instrument called the Team Steps, which was developed by the Department of Defense. And we get a pretty nice correlation here between neurodynamic measures. And the same thing on the left with a recently developed submarine team behaviors toolbox. And so this helps the validation point, as well as suggest that we actually may be able to develop objective measures. So, take-home messages: it is possible to model the second-by-second dynamics of teams and relate them to changes in the task and their activity. Frequency, magnitude, duration of the changes provide a quantitative framework for assessing team performance. And then finally, these intermediate representations seem to generalize across the many teaming situations, both healthcare as well as submarine, as well as high school. And so I'd like to give special thanks to Tricia Galloway, who works with me, for research support, invaluable research support, and the officers and crew of the submarine school and the hospital staff at the Order of St. Francis Hospital in Peoria. So with that, I think I'll turn it back over to Darren.
Did everybody get that?
No quiz.
So John Coleman's going to come up and talk more about the practical applications of some of the science that you just heard. So let's welcome him back to the stage. And I've also asked Dr. Stevens to chime in whenever he feels appropriate to do so. So he'll stay up here on the stage with us. Dr. Stevens, who wants?
Well, Professor Campen, thank you very much. We all have that urge to duck underneath television cameras, don't we? It's television cameras and helicopters. We don't need to duck, but we always do. I would personally like to thank Professor Stevens very, very much. He's come all the way from UCLA and is in the middle of all kinds of research programs and grants. The nature of, yes. The nature of the work that they do is very exciting. They have all kinds of research grants from people like the US Navy and DARPA, which is equally exciting, and that makes Ron the envy of many people in academia. But with those grants come high expectations. So we're very lucky to get him at all, and pretty soon you'll have to get back to work. How many people have heard of the American Psychiatric Association, the APA? Good, excellent. It's about 2/3 of you. How many of you have heard of a thing called the DSM? Excellent. The DSM, for those who don't know, is a great big blue book that contains every possible mental condition of thought, feeling and action. It stands for the Diagnostic and Statistical Manual. They're numbered. Right now we're at the DSM-5, and it contains all of the known mental illnesses and the diagnostics for that, and they're used primarily by psychiatrists and psychologists. Well, right now, as I say, we're on the DSM-5. Those are not issued on any particular schedule, but best guess, maybe 5 or 6 years until we see the DSM-6. The DSM-5 marks a seminal point in the evolution of the study of human thought, feeling and action. Why do I say that? Because there are commitments in the DSM-5 that say, and I'm quoting word for word here, that by the release of the DSM-6, Every single condition of thought, feeling and action will be diagnosed to the malfunction of specific circuits in the brain. In other words, they're throwing out all the old models, and team and individual neurodynamics is going to be the new model in the DSM. How they're going to do that in the time they have, I really don't know, but I think the message, Ron, is you better get to work.
I'm working.
So that's how serious this is. That's how real this is. I was asked to come up at the end and spend a couple of minutes talking about the practical implications. Now, my first question to you is, it may make some noise, but would you mind terribly much if I moved the microphone and came out where I can see you? I feel like I'm hiding back here.
I don't know if, yeah. Yeah, stay close to the mic.
Okay, hopefully that wasn't too obnoxious. Can you still hear me clearly?
Yeah.
Okay, that's wonderful. What does this mean for us practical people? Because that's where I live. What does it mean for the person who has to lead, who has to be a manager, who has to be an organiser, who has to run an enterprise or help someone in an enterprise right now, today, in the month of March, year 2016? Well, let me ask you a quick question. How many of you have heard the saying that the word team, T-E-A-M, stands for together everyone achieves more? Who's heard that one? Okay, that's about half of you. That's a favoured aphorism, a favoured cliche of team builders and team trainers and leadership trainers and goodness knows what all. T-E-A-M, together everyone achieves more. Well, guess what? You've just seen the evidence. There's absolutely no truth in that. Sometimes together everyone achieves less. That would be TEAL, T-E-A-L. Sometimes together everybody achieves nothing. I guess that would be TEAN, T-E-A-N. Now, what's fascinating about this is, let me ask you again for a show of hands. How many here tonight would describe themselves as working managers, working leaders, be you a frontline supervisor or the CEO? How many of you are working managers, working leaders? I hope you'll agree with me. Please come back later when we're done and tell me if you do or not. But that isn't what I see in the workplace, together everyone achieves more. That hasn't been what I've seen in the 30 years I've been in the workplace. I've seen together everyone achieving more sometimes, less sometimes, nothing other times, chaos other times. I guess that would be teak. But until now, there's not been the science to support your common sense intuition that that is in fact the situation. And that is not nothing, that is huge. It's very easy for us all, for example, to agree that the human being is not rational and that the thought processes that lead us to conclusions are generally not rational. It is entirely, that's something you can agree on with somebody over a beer in a bar, but it is entirely different to be able to prove that rigorously and scientifically, and that is what Daniel Kahneman did a few years ago, and he got the Nobel Prize for it. That's where team neurodynamics is headed. Here's another aphorism that needs to change. There's no I in team. Who's heard that one? There's no I in team. You've just seen neurodynamic evidence direct from the brain, not filtered through somebody's theory or agenda or viewpoint, that says there is an absolutely huge I in team. The I in team provides the flexibility, as it turns out. The only states that a team has that don't have the I are the states where the team is dormant, nobody gives a hoot, and the state where the team is collegiate. Everybody's equally engaged to about the same level neurodynamically. But every other state a team can be in depends on the structure of that team not being symmetrical. And it depends on you not being able to say the team this, the team that, because some people are high, some people are low, some people are in between. There's fine structure involved, and that's all about the I. The flexibility of work teams now seems to be to do with the I. That's new news. Here's another one. This is one of my favourites from Ron's research. One of the things Ron discovered is that when teams think they are about to succeed, they behave as though they already have. That's what he's calling the marker for anticipation. Mm-hmm. When teams think they're about to fail, they behave as though they already have. Again, any working manager in this audience knows that because you've seen it at work. But the science is only now catching up with you. And a lot of what's being taught out there is just plain wrong. Or, to quote Ronald Reagan, the problem with experts is they know a tremendous amount, but a lot of what they know just ain't so. That's changing very, very quickly now. Those of us who studied psychology in years past, if we haven't refreshed our understandings in the last couple of years, we're behind the 8 ball. So these are just some of the examples. The last one I'll leave you with before moving on to question time. Does that suit the timings, Professor Campen? Good. The last one I'll leave you with is this one. How do people learn best? How do people learn best in a team environment? Well, That gets complicated because in the real world, when people train and learn, they have to pay for it. Someone has to pay for it. If you're a student at Montgomery College, somebody's paying for that. It's not free. You're paying some, the state's paying some, everybody's paying something. So, therefore, the financial side of it gets involved. So, for example, it's very hard for me in the modern world to win an argument with an HR director that says, I want to give people team training, I want to take them all the way off site, I want to take them for 2 days. So we're up for airfares and hotels and 2 days off work, and it's going to cost $2,000 a head. And then along comes somebody else advising the same HR director and says, or you could go online and do it for $25 a head in an hour and a half. And the attraction to the manager is they get to check exactly the same box on their performance agreement. Did team building with the team. Tick. Now, that's not the industry's fault. That's our fault. That's our fault as trainers, teachers and learners. We've failed to distinguish those things which do not transfer well to the online world. Team neurodynamics, the application of science, can help us do that. One of the big things it's taught me is that simulation, which builds new neural pathways in the brain, seems to be the only effective way to train teams. If that wasn't true, you could be 19 years old, join the Marine Corps, of which Professor Campen here used to be a member.
Hoorah!
Thank you, Marine. Sit in front of a computer, do the online course, pass the exam, and then the drill sergeant says, congratulations, son, here's your weapon, you're a Marine. I don't think the Marine Corps is going to do that anytime soon, or surgical teams, or airline pilots, or police officers. And I don't think the role you serve in the workplace is any less critical than that. But if we don't bring the science, the economics will run right over the top of us. That's the thought I want to leave you with. And at this point, I think it's time for Q&A, Professor, is it not?
Great. Yeah.
A good question for the doctor. First of all, thank you, Professor, for a really enlightening presentation. My question has to do with having worked with many teams over my career. I've detected a bias, if you want to call it that, in the generations. So if I'm dealing with a team of experts that have 30-plus years of experience, and I have a group of young people that are in a different generation, have you seen that in your studies as far as a bias in how your neurological brain waves would work?
I'm going to ask them to come over here, and it's probably a better microphone.
Well, I think that's a fascinating question, but we have not had the opportunity to do that in our studies. So the submariners that we've been studying, they've all had 1 year at sea.
Right.
And now they're coming back in this advanced candidacy course and to become navigators and ship drivers. And so they are a very homogeneous population,
right.
Certainly with regard to gender, but also with regard to experience. Hospital, we have studied fourth-year medical students and have begun doing comparisons with experienced operating room teams. There is a detectable and significant difference between these two groups, which accounts for the validation studies that I showed on the last slide. We are not to the point of doing mixed team studies yet, but when I mentioned that being able to quantitate the effects of experience now means that we can start changing training protocols in a scientific way and begin to show the effect when you do have mixed teams like this. I think that one's, that's low-hanging fruit. That's really important question to answer right away.
Very good. Thank you. Appreciate it.
All right. Next person has a question.
Thank you. Social scientists Moore here. Are there applications for this type of research in family dynamics as well? It seems they're teams, they're not always goal-oriented, but are there applications for family?
Yes. I I'm just guessing.
Thank you.
Gets up,
yeah.
says yes, sits down.
Yeah, I think there actually are. And, one of the lessons that we've learned is that teamwork is not packaged within each individual. It emerges from the interactions, short-term and long-term, of these individuals. And so you do get into chaotic attractor states. And we see this, it's some modeling I didn't want to show today. Chaotic attractor states are very common, they're highly documented in the literature. And a lot of therapists come in there to try to find ways of kicking families off of it and going into different types of dynamics, getting out of these attractors. I think we got a ways to go before EEG would be accepted by a family that's having some difficulties. That would probably be the big challenge. But I think it would actually be fascinating because EEG may give you a longer prediction line before actually crises happen.
So, Rebecca, you have a question?
I do have a question, and I think this may be a question for John, but it might be for either one of you. So I also work within teams, both as myself as a team member and also helping other teams kind of come together. And I'm just wondering how important is the face-to-face piece of it? Because a lot of teams these days are virtual, and I see some of the same dynamics that you're talking about, even in like an online team when you're doing a project that way. So I'm just wondering if you have any insight.
Okay, I'll kick it off, but please interrupt if you wish.
I can kick it off.
Kick it off.
How many people here have seen the movie Hitch? How many people remember the first opening monologue when he goes on and talks about that 80% of human communication ain't coming out of your mouth? That's the part that you get from the face-to-face interaction. And so as soon as you remove that, even with synchronous communication, what you're doing is you're throwing off the rhythm. Your teamwork is built on this gigantic stack of social coordination that everybody has experienced all their life. And with teamwork, what you're trying to do is take this very, very small slice and bend this experience into a team experience, which is a much more formal type of interaction designed to accomplish a goal. So you have all of this other lifetime baggage that you have to bend and surrender in order to get there. A lot of this is just implicit. It'll be an eye blink, it'll be a flick of the hair, it'll be a little arm gesture, and a lot of that you sacrifice with virtual.
I couldn't agree more, and to that I'll add as a practitioner that learning that happens in one emotional state is not necessarily remembered or used in a different emotional state, and that learning that happens in one situation is not necessarily remembered or used in a different situation. Put it differently, I've been a volunteer firefighter for 15 years. I have never remembered the content of a single online course when stuff was falling on my head. What I've remembered is the practical rehearsal, done time and time and time and time again until you get so sick of it. But what you're actually doing is building new circuits in the brain. The brain doesn't work like a computer. It doesn't load new software. It builds new circuits. There's specific new circuits that are learned with learning. No circuits, no learning. So I would argue that online is great, but that the pendulum will swing back and that there will be at some point further balance, and that any kind of training that is to do with leadership, with picking up micro cues, with the warmth of a human touch, the many expressions on a human face, the way a person walks, their tone of voice, their posture, their behaviour, the way they move their body in space, and a half dozen things I or any other experienced leader could list, are all absolutely vital and cannot be successfully duplicated by removing sensory modalities. It's a case of the more the better. Or to put it differently, and in the words of the great American philosopher Mike Tyson, everybody has a plan until they get punched in the face. That's why you simulate. That's why you can't do all your learning as a disembodied mind. We're not disembodied minds. We're one piece. We're physiological animals. Thank you for the question.
Great. So if you don't mind, I'll ask a question now. Either one of you can respond. The press has already asked you if we're heading towards a dystopian future in which people will have to wear electrodes on their heads in order to get a job and to keep a job. What are your comments, responses to that?
Okay, Ron kicked off the last one. I'll kick off this one, but I hope that Ron comes in then.
Oh, yeah.
This is a common media question, would be my answer, again, as a practitioner and someone who talks to the media. That question's asked because it's sensational and sells newspapers, but it's still important to have a good answer to it. Are you going to have electrodes connected to your head in the not-too-distant future before you can get a job, before you can keep a job, before you can get certain kinds of health insurance, before you can keep certain kinds of health insurance, particularly coverage for mental health? I think that's highly unlikely. The emergence of technologies doesn't sweep away the principles of human society that have evolved hitherto and the principles of decency. There are many technologies and methods out there now that would be unacceptably invasive to human beings and which accordingly are not used for that purpose. I think that's what's going to happen. The reality, much more likely, what's happening now is that the insights about human cognition, human thinking that are derived from research of this kind, and it's not just EEG, there are PET scans and other kinds of ways of looking at the brain. This is about science, and the science and knowledge that's derived from that helps us understand better what it means to be human, what it means to work collaboratively in a team, how things can go wrong when they do go wrong, how they can be put right when they do go wrong. I would challenge anybody to come up with an example of a time when intellectual pursuit and knowledge in human history has had an overall harmful effect. Generally, it has a beneficial effect. The more we know, the better we do. And that would be my response to the question. That said, the journalist still wants to imagine electrodes on people's heads. Ron.
Well, having worked with medical students for a decade, having taught medical students for a decade, the high end are always going to get their hands on whatever is going to give them an edge. And so if EEG proves to give them an edge, then people will seek it out to grab a job, to hold a job, to develop new jobs. And right now, the market for brain-enhancing software is going wild.
Yes.
There was an article in Science magazine in January about federal regulators taming the brain's Wild West. And the Federal Trade Commission has fined Luminosity $2 million because they felt that their claims really weren't substantiated by the research base that they had. And so it's incumbent on people developing anything related to brain and neural training to validate it. And you don't often see many published research studies that come out substantiating the claims. Most of the brain exercises that you'll get will help you solve their exercises better and faster, but they may not generalize to more general cognitive functions or workload and brain enhancements. So that's where the objective, validated, reliable the science comes in. You got to make it quantitative.
Okay, Gary, we
I
got
think I
another
see a
question from the audience.
Hi, I'm in HR. We hire trainers, and we also do training. And this is really good news. That there's always pressure to put things online, and we have to kind of stand firms sometimes that training people in organizational culture, in working across cultural differences, in teamwork, needs to take place in simulations, in classes, et cetera. So I really appreciate it. I'm going to take this back to my supervisors and boss. I was wondering particularly about cultural diversity training. Is it an analogy that brain circuits are like our stereotypes or bias or messages that we received, and to disrupt those by teamwork or by exposure is how people learn to let go of those kinds of things?
Do you want me to start, or would you?
I think so. That's a bit outside my field, as we're not doing that type of training.
I think this might lead to a comment from Ron, because it's going to get back to neurodynamics, but we'll see. The question, as I understand it, had to do with cultural diversity. Cultural diversity to me is fascinating because of the way in which the brain works. We think the brain, for example, is built to work accurately. It is not. It is built to work quickly. Given the choice, the brain will sacrifice accuracy for speed all day long, because speed has conferred evolutionary valence on us. Likewise, the brain is not designed to remember. The brain is designed to forget. People who cannot forget can literally tell you what they had for breakfast on the 4th of July 1995, assuming they were alive then. They are fascinating to talk to, but those people are quite severely mentally ill. They cannot function in the world. So now you're asking about people reaching unfortunate conclusions very quickly. They may be very unfair and very inaccurate. It is my view that there is a natural tendency toward categorisation that people have cognitively that can confer tremendous power and efficiency on the brain. We have no understanding how the brain is efficient and as powerful as it is, but the shortcuts can have real problems, and this is one. How do you fix cultural diversity issues? How do you encourage cultural diversity, get people to uphold it? There are only 3 techniques I've ever used with groups in my job in 20 years that have ever worked, and the 3 techniques are 1, practice, 2, practice, and 3, practice. Building new circuits. Professor, anything to add to that?
No, not really, because that seems to be more related to individual cognition and not necessarily team cognition with the types of things that we're doing. So it's too far to extrapolate here.
But if your supervisors are asking, can that be done on an online course, my answer to you is that if the intention is to pass the exam at the end of the online course, you bet. If the intention is to not fall into bad habits on the worst day of your life, when you least feel like being a leader and you have a toothache, and person A wants to punch person B's lights right out, it will not help you one tiny little bit. The only thing that will is simulation and rehearsal, and that means that you have to invest in more than online training.
All right, another question from the audience?
As someone who intends to work in the field of psychology in the future, I was wondering whether or not you think this could ever be applied in like a biofeedback perspective to kind of help teams work together better.
Yep. I mean, that's our short-term goal, is to actually be able to deliver feedback of what went on during the simulation to the instructor before the debriefing begins. For instance, there's a sense that there are things that the team is perceiving and experiencing that aren't overtly visible to the observers. And if the observers knew that at this particular point in time, even though everything looks good, the team was actually under stress, I think that would greatly benefit and improve the efficiency of training. As far as feedbacking to the team as a whole, my sense is from mapping our neurodynamics onto team performance and periods of stress, the teams know that they've gotten into trouble. They don't necessarily know how they got into the weeds, but they know they're there. And so the big thing for us would be to figure out how they're going to get out. And I think it may be from the organizations that we see in subunits of the team we can get a better idea of how to quickly get them back into sync and get them out of it, like the experts do. The experts will get into trouble, it'll be a little blip, and they're out of it, and they're well on their way again. But the inexperienced teams, we've seen some dwell for 8 to 10 minutes before they actually got on the same page again. So that type of feedback, I think, would be very critical.
All right, we're going to take one more question from the audience, and then we're going to wrap it up.
I was interested in the alpha and the beta portion of it as you begin to discuss that. And have you looked at the social intelligence or the social relationship of the team and how they operate, and just what effects or what conclusions have you deduced from either high social IQs or low social IQs?
We have not had access to those records. For our human subjects approval, our approval is for going in there and being a fly on the wall to the extent possible and leaving with the data that we have. So as far as prior measures, individual measures or team measures, we haven't had access to that.
All right, great. I'd like to thank our guests for a fascinating presentation tonight. Let's give them a round of applause.